What's up, bitches? So the first step for the Bode plot diagram is that you have to convert your transfer function into this form right here, where anything that's getting multiplied in the parentheses has to be plus 1, denominator and numerator. For example, if you have a transfer function like this, you have to convert the 2, the 100, and 4 into ones, okay? And the only way to do that is just to factorize them out. So 1,000 times 2. Here we factorize the 100. And finally, you factorize the 4. You combine everything and then you just simplify it. All right, and in this case, here this is supposed to be a 2. That's your 0. This is your pole. There's another one of your pole. The second degree polynomial, I'll explain in a second, and this would be your gain. So once you've completed step 1 and you have this form, now we could start constructing the Bode plot. In the Bode plot diagrams, you're going to have two plots, one for magnitude, the other for the phase angle. These are going to be on your log scale, and usually the way I draw them is at the origin over here. I start with 0.1, and then it's going to start like something like this, and then 1. Start like this, and then 10. I go up until 100 for the magnitude, and 20 and 40. -20, -40. For me, I didn't really need to go beyond these, but in your case, if like you have a specific case where you have to go beyond these to construct the Bode plot, you can go beyond this. It's just, I find it way simpler for me. It's the same thing for the phase angle. It's going to look like something like this, but usually during your exams, your professor is going to give this to you already. It's going to look something like this. And for the phase angle, I go up to 90 up until 180. -90, -180. Once you have the magnitude and the phase angle logs, because some questions you're going to have to make these yourselves, but usually your professor is going to give you already the graph. But then you have to follow these 5 next rules that I'm going to explain to construct your Bode plot. All right, so rule number 1 for the K, for your gain, you have to calculate 20 times the log of K. Okay, you're going to get a constant. Whatever that constant is, for your magnitude, it's just going to be like a straight line. Okay, it's not necessarily 20, it's just whatever 20 times log of K is. And for the phase angle, the gain has 0 effect. It's just going to stay 0. All right, so you have to draw this for the K. So for example, in the transfer function that we have, the K is 5. So we have to calculate the 20 times log of 5. And that's going to give us a value of about 14. It doesn't need to be super precise. You're just building the Bode plot. So we would have to draw 14 on the magnitude. And the phase angle, it has 0 effect, so we could just ignore it and move on. All right, rule number 2 are the zeros. This is what you'll find in the numerator. For the magnitude, yeah, it's 0 up until z, the value of z, whatever it is. Let's say in this case it's at 1. All right, after 1, it starts to increase at a rate of 20 decibels per decade. So in this case, decade, it doesn't mean 10, like just the value 10. It means 10 times the frequency. This x-axis is the frequency. An easy way for me to remember is I just take, I take this, the z, and I do times 10. So here would be 10 over here. And by the time the frequency is 10, it would have increased to 20. And then you just draw a straight line. Plus 20 dB per decade. For the phase angle, let's say again our z is, let's take, for example, z is 2. All right, here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If it's 2, it's 0 up until 0.1 z, or the 10th of z, okay? which would be 0.2 in this case, it's going to increase at a rate of 45 degrees per decade, up until the 10th of z, 10z, all right, which in this case would be 20. This is 2 decades, so by the time it reaches 10z, it's going to have increased to 90 degrees. So you draw a straight line like this. Beyond 10z, it just continues a straight line like this. So in our example, the z is 2. So for the magnitude, we would have to draw 0 up until 2. And beyond that, it continues upwards to, and the slope is 20 dB per decade. For the phase angle, same thing. You take the 10th of 2, so 0.2. It's going to increase up until 20, because that's like 10z. By the time it reaches 10z, 20, it would have been at 90 degrees, and then beyond that, it just continues as a straight line. Rule number 3 is the poles. This is what you'll find in the denominator. It's the same thing as a z, except instead of going up, it goes down. So it's going to go up until 1, for example, if p is equal to 1. And by the time it reaches the 10th, so 1 times 10, it's going to be at negative 20. So it's going to continue a straight line like this. This is, for me, the easiest way to remember. For the phase angle, same thing. If, let's say, p is equal to 5, you take the 10th of 5, so 0.5. This is 0.1, 0.2, 0.3, 0.4, 0.5. It's 0 up until 0.5. And then here would be p. And 1, 2, 3, 4, 5. Here would be 10p, right? 2, 3, 4, 5. Yeah. By the time it's at 10p, it would decrease to negative 90. You draw a straight line, and then you continue straight for the rest of the frequencies. Just keep in mind for the phase angle, your slope is negative 45. Whoops. Where is it? Negative 45 degrees per decade. However, because here there's 2 decades over here, that's why it's going up to negative 90. Here it's negative 20 decibels per decade. So back to our example, our p is 4. So for the magnitude, we're gonna draw 0 up until 4, and then we're gonna draw a slope of negative 20 dB per decade. Phase angle, same thing. We're gonna take the 10th of 4, so it's 0 up until 0.4. Then we're gonna take p, which is 4, we're going to do times 10, 40. By the time it's at 40, it's going to decrease to negative 90 degrees, and then we're going to draw a straight line beyond that. Rule number 4 is your pole at the origin, if you have 1 over s in your function. In this case, your magnitude, it crosses this point, 1 and 0, and it's just a slope of negative 20 decibels per decade for the whole thing, okay? But here, since we're starting at 0.1, I always put 20, and then it's just a straight line forever. For the phase angle, it's negative 90 constantly forever. Now, this is how I remember, but just pay attention. If, for whatever reason, you started your log scale at 0.01, then this would start at 40, but still the slope would be the same, negative 20 decibels per decade. So in our example, we do have a 1 over s over here. So to take that into account, we take the magnitude at 20, and then we draw a slope of negative 20 decibels per second. For the phase angle, we just draw negative 90 all across. Now, in your transfer function, if you have this, 1 over s squared, it's the same thing, except like it crosses 1, for the magnitude, it crosses 1 and 0, except instead of being negative 20, it's negative 40 decibels per decade. It's just a steeper slope, negative 40 dB per decade. And for the phase angle, same thing. Instead of negative 90, it's double, it's negative 180 all across. Rule number 5 is your complex poles. This is probably the most complicated one, but it's not that hard. You have to transform it into this form right here. So let's say, for example, you have a form like this in your transfer function. This is your standard second degree polynomial. You have to transform this part into 1. So all you have to do is divide by the natural frequency squared. So you're going to get this. Once you have this form, you could follow rule number 5. Rule number 5 says that for the magnitude, it's 0 up until the natural frequency, okay? Pay attention. Over here is your natural frequency squared. What you want is the normal one. Okay, so let's say, for example, here it's equal to 1. It goes up until the natural frequency and then decreases at a rate of negative 40 decibels per decade. Okay, so by the time it reaches like the 10 times its value, which is 10 for example here, it's gonna be negative 40, and then you just draw a straight line forever. For the phase angle, it's the same principle. It's just let's say here the natural frequency is, I don't know, 5. 2, 3, 4, 5. You're going to take the tenth of it, 1, 2, 3, 4, 5, 0.1. It's going to be 0 up until that point, and then it's going to decrease at a rate of negative 90 degrees per decade. And since there's 2 decades here, by the time it reaches 10 times the natural frequency, it's going to be negative 80. No, sorry, negative 180 degrees. Beyond this, it just continues a straight line. So in our example, we have s squared divided by 100. This is your natural frequency squared. We want the normal natural frequency, so you just do the square root, equals 10. Now, for the magnitude, you start at 0, you go up until 10, and then decrease at a rate of negative 40 decibels per decade. Phase angle, same thing, there's 10, right? But now you have to take the tenth of it, so 0.1 times 10, 1. Phase angle starts at 0 up until 1. Then you do like times 10 for the natural frequency. 10 times 10 is 100. By the time it's at 100, it's going to decrease to negative 180 degrees. You draw a straight line, and then beyond that is just a straight line. So at this point, we've covered the gain, the zero, the pole at the origin, and complex. There's no other rules to follow. I just took this example because it's the most complicated one and it covers every rule. But you have to apply those 5 rules until you cover all of these parts. Once you've completed this, you've completed step 2. We could move on to step 3 to finally start drawing the Bode plot. I'm going to start with the magnitude. I've just increased the scale to go to frequency up into 1,000 and increase the decibels to at a range of negative 60 to 60, just so it's easier for you guys to see. So for step 3, you have to start adding on this graph right here. You have to start adding all your plots, all of the things that you've drawn before, right? So for the magnitude, we've drawn the K, which was 14 constantly. We have the 0. We have the pole. We have the pole at the origin. And then we have the complex poles. All right, now, once you have everything on your Bode plot, you have to draw the sum of these, okay? Which is just a fancy way of saying, like, whatever value it is at that frequency, that's your, like, the fucking Bode plot. So, for example, at the beginning at 0.1, we have the gain, that's 14, and because of the pole at the origin, that starts at 20, you have to do 20 plus 14. So our Bode plot is going to start at 34. And then for the gain, it's just a constant, so you could just ignore that. It's just a straight line. You could see that from the pole at the origin, it's a, It's a fucking slope at a rate of negative 20 dB. So you just draw a line parallel to that. Simple as that. You draw that up until 2. At 2, we have the 0 that starts increasing. Therefore, that's plus 20 dB, and the other one, this other line is negative 20 dB. So that just cancels out. So it's just constant, a straight line. Up until 4. After 4, you got your normal pole, the 4, that makes the Bode plot go at a rate of decrease at a rate of negative 20 dB. So you're going to draw that, and then at 10, we could see that there's this other line, the complex poles, that makes it go to negative 40 dB. So you already have the negative 20 from the negative 20 rate from the poles and the negative 40 rate from the complex poles. So beyond 10, it's going to decrease at negative 60 because both of those are combined, right? So beyond that, it's just negative dB, a straight line. That's it. Now for the phase angle is a little harder because for the magnitude is just beyond once you reach that certain point for the pole or zero, it's just a straight line. But the phase angle, it goes up until 10th of that and then continues a straight line. So it's a little more confusing, but we'll go step by step. First of all, we could see that it starts at -90 because of the pole at the origin. So we start at 90. Once it reaches 0.2, there's the zero that's involved, and it increases at a rate of 45. Okay, so we just draw a line parallel to that. At 0.4, there's the normal pole, that's -20 dB, so that cancels out the zero, so it continues a straight line. At 1, there's the complex poles, causing it to decrease at a rate of -90. So you're going to draw a line parallel to that. By the time you reach By the time you reach 20, the effects of the zero fade out, right? It just continues a straight line. We could see over there. So you have to take that into account. So it starts to decrease another 45 degrees per decade. So you're going to draw a line a little more steeper. And then by the time you reach 40, the effects of the pole at 4 fade out. They just continue a straight line. So you have to take into account. So now it starts to decrease 45 degrees less, so it's less steep. So it goes back to -90 dB per -90 degrees per decade. Once you reach 100, the effects of the complex pole fade out, and it just continues a straight line beyond that. So whatever is in red is your Bode plot for the angle, and that's it.